Today, we are going to peel back the layers of reality, zoom past the limits of human vision, and explore the mind-bending architecture of the modern solid-state drive. This isn't just a story about technology. It's a story about how humanity learned to trap lightning in a jar and teach it how to remember. We live in an era of a strange modern paradox. We are producing more data than at any point in human history, yet our storage devices are shrinking. If you look back just 30 years, storing 20 gigabytes of data would have required a hard drive the size of a shoebox, spinning at thousands of rotations per minute, humming with the sound of mechanical effort. Today, that same amount of data and 1,000 times more fits onto a micro SD card no larger than your fingernail. This isn't just a feat of manufacturing. It's a total reimagining of how we interact with reality. When we look at a solid-state drive, SSD, or the internal storage of a phone, there are no moving parts. No spinning platters, no mechanical arms. It looks like a silent, inanimate object, but this silence is deceptive. Inside, there is a bustling metropolis of electrical signals, a high-speed ballet of electrons that makes the busiest city on Earth look like a sleepy village. To understand how this works, we have to look past the casing. We have to stop thinking in inches and start thinking in nanometers. We have to accept that the files we see on our screens are mere ghosts, beautiful illusions created by a physical architecture so small it borders on the impossible. Imagine you have a shrink ray like in a science fiction movie. As we zoom into the heart of your device, the plastic and metal exterior begin to look like vast, jagged mountain ranges. We pass through the protective layers and enter the silicon die, the brain of the storage system. Here, we encounter the vertical NAND, or V-NAND. In the old days of computing, memory cells were laid out flat like a single-story parking lot. But as we demanded more storage, we ran out of land. Engineers realized they couldn't keep making the parking lot wider, so they did what architects in Manhattan did. They built up. V-NAND is essentially a microscopic skyscraper. These structures are vertical because they stack memory cells on top of one another in layers. It is a nanoscopic city where the buildings are only a few hundred atoms wide. This is where your data lives. It isn't stored as ink on paper or grooves on a record. It is stored as electrical states. Your wedding photos and your favorite songs are, in their most fundamental form, trapped clouds of electrons hanging in the void of a silicon skyscraper. To truly appreciate this, we have to understand the bridge between our world and the digital one. Let's take that photo you took earlier. To your eyes, it's a beautiful gradient of colors. But the computer sees something entirely different. When you hit save, the camera sensor breaks that image down into a grid of millions of tiny squares called pixels. Each pixel is just a set of instructions. It says, give me this much red, this much green, and this much blue. These levels are assigned numbers. But the storage doesn't understand the number 255 or 128. It only understands two states, on or off. High voltage or low voltage, 1 or 0. This is the binary system. Through a process of digital alchemy, the vibrant colors of your life are distilled into a relentless stream of ones and zeros. What feels like art to us becomes pure, cold data to the machine. A single high-resolution photo is transformed into a string of binary digits so long that if you printed them out on paper, they would stretch for miles. And yet, the V-NAND structure swallows this massive sequence in the blink of an eye. As we zoom back out for a moment, the sheer scale of the challenge becomes clear. A modern 1 terabyte SSD can hold roughly 250,000 high-resolution photos. That is trillions of bits. The hardware must not only store these trillions of bits, but also be able to find a specific one, say, the bit that defines the color of your mother's eyes in a photo from 2018 in a fraction of a millisecond. The challenge isn't just space. It's reliability. Unlike a book which stays the same once printed, digital memory must be fluid. We want to write data, read it, and then erase it to make room for something else, all without wearing out the physical structure. How do you build a container for a trillion invisible things that doesn't leak, doesn't break, and responds instantly to your touch? This is where we meet the citizen of our nanoscopic city, the fundamental memory cell. The foundational unit of all modern storage is the charge trap flash memory cell. Think of this cell as a tiny, sophisticated bucket. But instead of water, this bucket holds electrons. In the early days, a cell was either full or empty. If it had electrons, it was a 0. If it was empty, it was a 1. This is called single-level cell SLC technology. But engineers are never satisfied. They realized they could store more data in the same amount of space if they could measure how much water was in the bucket. If the bucket is 25% full, that's one piece of data. 50%? Another. 75%? A third. By precisely controlling and measuring the number of trapped electrons, modern multi-level cells, MOC, TLC, or QLC, can store 3 or 4 bits of data in a single microscopic cell. This is like being able to tell the difference between 1,000 electrons and 1,001 electrons. The precision required is staggering. It is like trying to fill a swimming pool to exact millimeter while a hurricane is blowing. One of the most magical things about an SSD is that when you turn your phone off, the data stays there. It doesn't evaporate. This is called non-volatile memory. In a charged trap cell, the electrons are held behind a tunnel oxide layer, a physical barrier that acts like a high-security fence. When you write data, the system applies a high voltage that pulls electrons through this barrier using a phenomenon called quantum tunneling. Once they are inside the trap, they are stuck. They can stay there for years without a power source. Reading the data is gentle. The system sends a small electrical pulse to see if the electrons are there, like a guard tapping on the bucket to hear the sound it makes. But erasing is a violent act. To clear the memory, a massive reverse voltage is applied, literally yanking the electrons back out through the barrier. This process is so intense that it eventually causes microscopic wear and tear, which is why your storage devices don't last forever. They are slowly, atom by atom, being worn down by the very act of remembering. Now, let's look at how these cells are organized. They aren't just scattered randomly. They are stacked in strings. Imagine a long vertical needle. Each needle contains dozens or even hundreds of these memory cells stacked one on top of the other. By stacking them vertically, we save an enormous amount of floor space on the silicon chip. This is the secret to why your phone can have 512 gigabytes of storage today when 16 gigabytes was the limit a decade ago. We haven't made the chips bigger. We've made the towers taller. Each layer in this vertical string is connected to a control gate. This gate acts like a door. When the computer wants to talk to a specific cell on the 50th floor of the 1000th tower, it sends a signal that opens that specific door while keeping the others closed. It is a level of organization that makes the world's most complex logistics companies look disorganized. As we expand our view, we see that these strings are grouped into larger units. A horizontal slice across many strings is called a page. This is the smallest unit of data that can be written at once. Think of a page as a single sheet of paper in a book. Multiple pages are grouped into blocks. This is where it gets tricky. While you can read or write a single page, you can only erase an entire block. Imagine if you wanted to change one word in a notebook, but the only way to do it was to erase the entire chapter and rewrite it. This is exactly what's happening inside your SSD. The example structures we've discussed are just the basics. In a real-world chip, the scale is mind-boggling. We aren't just talking about 10 or 20 layers. Modern V-NAND chips now have 176, 232, or even 300 layers. Within a single square millimeter of silicon about the size of a pinhead, there are billions of these cells. To connect them, engineers have to drill millions of microscopic holes through the stack of layers. These holes must be perfectly straight and uniform, even though they are thousands of times thinner than a human hair. If one hole is slightly off, the entire chip is useless. This is the pinnacle of human manufacturing. We are no longer just building machines. We are sculpting the atomic structure of matter to serve our need for storage. Why does your phone feel so fast? It's because of parallelism. When you open a large app, the system doesn't just read one cell at a time. It reads thousands of cells across hundreds of blocks simultaneously. By using bit lines and word lines to coordinate data flow, the SSD can achieve transfer speeds of several gigabytes per second. This means the entire text of the Encyclopedia Britannica could be read in a fraction of a heartbeat. This speed is what allows us to stream 4K video, play complex games, and multitask without a hitch. It is the result of precision timing and electrical orchestra where every instrument must play its note at the exact nanosecond required, or the entire symphony of data falls into chaos. The final step in creating high-density storage is packaging. Once the individual silicon chips are made, engineers don't just put one in a device. They stack the chips on top of each other inside a single black casing. An interface chip sits at the bottom of the stack, acting as the translator between the memory cells and the rest of your computer. This interface chip is the diplomat, taking the high-level commands from your operating system. Save this TikTok video and translating them into the trillions of electrical pulses needed to move electrons into their traps across multiple chips. This multi-chip package is what allows a single SSD to reach capacities of 4 terabytes, 8 TB, or even 30 terabytes in a form factor that fits in your pocket. As we step back from our nanoscopic journey and return to the human scale, it's worth reflecting on what we've seen. At its heart, everything you do online, every email, every like, every digital memory rests on the shoulders of trapped electrons and binary logic. The story of storage is a story of human ingenuity overcoming the limits of the physical world. We wanted more, so we went smaller. We ran out of room, so we built up. We faced the limits of physics, so we harnessed the strange behavior of quantum tunneling. It is a testament to the fact that complexity and simplicity are two sides of the same coin. The concept 1 south and 0 south is simple. The execution trillions of cells in a vertical 3D lattice is a masterpiece of engineering. The story of V-NAND teaches us that when we face a wall or a limit in our lives, the solution often isn't to push harder against the wall, but to change our perspective. When engineers couldn't go wider, they went vertical. In your own life, when you feel stuck, ask yourself, am I trying to build on a flat plane when I should be building a new dimension? Progress often requires us to look at the invisible details we usually ignore. Because these memory cells are worn down by erasing and writing, your devices have a finite lifespan. To keep your data safe, remember the 3-2-1 rule. Have 3 copies of your data on 2 different types of media, like an SSD and a cloud service, with 1 copy kept off-site. Treat your storage with respect. It is a physical object doing an impossible job. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.